Hello everyone, my name is Ali Turani and I'm going to present you our paper titled Vision-Based Situational Graphs, Generating Optimizable 3D Scene Representations. Vision sensors are able to supply rich visual information and enabling the extraction of semantic information through processing visual data. Accordingly, fiducial markers are the tools that can aid visual SLAM systems in detecting semantic entities while reconstructing a map due to their unique identifiers and can provide valuable pose information. Although there are some marker-based visual SLAM frameworks out there, such as UCO-SLAM and TAG-SLAM, they purely create geometric map representations. The main motivation for the current work is to implement a marker-based optimizable visual SLAM that creates accurate maps from the environment through adding new semantic and geometric constraints for such accuracy enhancement. The framework also augments hierarchical representations to the reconstructed map using semantic entities. Here you can see the pipeline of the proposed method and its constituent components. The framework is built upon ARG-SNT-UL 3 and benefits from a multi-thread architecture for processing data. The generated situational graph of the proposed approach is depicted here. You can see that it incorporates semantic constraints including walls, doorways, corridors, and rooms. The pre-existing geometric constraints have been complemented with semantic constraints acquired with the aid of fiducial markers. Additionally, introducing a new generation of markers that are imperceptible to humans but visible to robots under certain lighting conditions with a specific camera setup, along with validating their applicability in robotics, is another contribution of this work. For evaluating the performance of the proposed method, labeled as Visual S-Graphs, a 3D LiDAR sensor and an Intel RealSense depth camera were mounted on two-legged robots. The robots collected data provided by sensors while traversing various indoor environments with different configurations. Each wall and door of the environment were labeled with printed ARG markers, and the unique identifiers of the markers were stored in a database to fit the method. Accordingly, various experiments have been done on the proposed approach, UCO-SLAM as a marker-based visual SLAM, semantic UCO-SLAM, and ARG-SNT-UL 3 as the baseline. Also, due to less noisy outputs of LiDAR sensors compared to vision-based sensors, S-Graph Plus as a LiDAR-based framework has been used to produce ground truth data. We can see that Visual S-Graphs outperform its baseline counterpart and other frameworks across various scenarios. This enhancement can be attributed to the ability of Visual S-Graphs to introduce new constraints to the map through the association of semantic entities. It should be noted that some of the markers employed on door frames was imperceptible, and given that the sole distinction between such markers and ordinary ones lies in the detection step, the resulting semantic map remained unaltered.